So perhaps you can see just my browser, and there's the web page of Tony Appello up on the screen. Hopefully you can see that. Yep. So Tony Appello is one of the authors of PHREEQC, the other being David Parkhurst. I'm not sure entirely of the exact lineage of the code, but I believe that they developed the software while they were both at the USGS. David Parkhurst, as far as I know, is still there, or at least has some affiliation. But the years have rolled by since this was first put together. So I know that Tony Appello now resides in Amsterdam, and he runs courses in PHREEQC. And over time, the code has been augmented to include more types of problems and different kinds of systems. So originally, it was essentially a low temperature aqueous geochemical code. So that's basically geochemics speak for surface water environments, which are, or near surface environments, which are as close to thermal conditions, like sort of normal room temperature type conditions. And now subsequently it's been expanded to incorporate high temperature pressure systems. So you can actually do an awful lot with the code in the hands of an expert like Tony Appello. So hopefully I can give you some useful pointers to get started in using PHREEQC for Speleothem applications, and point you in the right direction for more sophisticated applications. Now, I became aware of PHREEQC during my PhD with Ian Fairchild, and Ian used a code which is actually an earlier, I believe, version of this called Mix4, which supports some of the functionality that PHREEQC has, but is much more constrained in the range of types of reactions and physical processes that it can simulate. And Ian always said PHREEQC is kind of like the gold standard. Go there if you want to learn, geochemical modeling. And I picked up what I know from a guy called Martin Anderson, who was at the University of New South Wales. And it was really through his affiliation with Andy Baker, and I worked there as a postdoc for a bit. So I picked up some stuff, and his supervisor, DK Postma, wrote this book with Tony Appello. So that's kind of the lineage. The experts are definitely the people at USGS and Tony Appello as well. So I'll do my best to give you some good pointers. There's actually a lot of helpful stuff in the code as well, if you know where to look. And so I can see that Yuval is commenting on the code. We can talk about that later. Yeah, so there's a lot it can do, and it's been developed principally with groundwater systems in mind, and what our hydrogeologists refer to as porous media. So, a porous medium is something like a sandstone, which is quite homogeneous, and that allows for certain assumptions to be made about the characteristics of flow and reactions in those systems. Obviously, a karst environment is a multi-porosity system with the matrix porosity, there's fractures, and there's conduits. So there's huge variability in how water moves through a karst system. And equally, unlike in porous aquifers, where essentially once you move beneath the vadose zone into the phreatic zone, which is the area where the voids are filled with water, so the true groundwater, in those systems, multi-phase flow processes, etc., are less likely. That tends to happen in the vadose zone. Caves are developed in the vadose zone, or at least active vadose speleothem forming caves, which are where most of us will want to look and do our research. In those settings, you can have very complex flow processes, multi-phase flow, so gases and waters interacting in situ. And so this gives rise to some of the processes that we observe, and we infer from monitoring drip waters. So we can infer, for instance, that waters have evolved and degassed and precipitated calcite, for instance, along the flow path to a speleothem. So clearly within the epicast, we have gas and liquid present together. And then again, within the cave, as a drop emerges in a cave, then there's a huge atmosphere present for which the water to find a new equilibrium. So caves are not an obvious and perfect application or case for this code. So it's important to bear that in mind, what it's designed for, and then putting it to use with a knowledge of that. Okay, so I'm just going to step through some slides to give you a little bit of background, and then we'll crack on with the code itself, and I'll hopefully be able to give you some useful examples and pointers. I'll also just now, while I've got you, before I launch into it and forget, I'm going to stop the share on that. Okay, so this is a picture from Waipuna Cave, which is where we've done quite a bit of work recently in collaboration with our colleagues in Europe, Seb Breitenbach in particular, and we've done lots of monitoring there. And I'm going to, in the link, the spreadsheet, which Seb has now posted on the chat, there's some an example which we're going to work through, which has some data from Waipuna. So it's not just numbers we've made up, this is real data from a real cave. And so before we start with the modeling, we need to just cover off a few basics so that everybody sort of is familiar with some of the terminology and the principles which I'm going to use, because I can't really assume a great deal here. So we're just going to run through these points. The law of mass action and what we mean by that, what a saturation index is. We hear that bandied around quite a bit, but maybe you don't know. Some essential assumptions that we make in our modeling, which include the fact that the system, the water, is in electrical neutrality or equilibrium, and a point on units, and then a little bit of a step through speciating, what we might say speciating water. I'm also going to just very quickly touch on what PHREEQC actually does, as I understand it, not being a coder myself. Okay, so to begin with, let's just nail what we mean by equilibrium. An equilibrium process in chemistry is just defined by the fact that the process goes in both forward and backward directions. So there are processes or reactions that proceed only forwards. So let's say we dissolve some strong acid into water, that goes to completion, and there is no reverse reaction. The carbonate system, which we're all working with, is an example of a weak acid-base system, which is defined by equilibrium processes. So a good way to illustrate this perhaps is to imagine water in a beaker with a chunk of limestone at the bottom. That limestone will reach equilibrium, or you could also call saturation with respect to calcite. So what will happen initially, if the water is pure, is that the mineral will start to dissolve and calcium and carbonate ions will go into solution. Eventually, the amount of ions that can be held by the solution will be met and will be at so-called equilibrium. But the chemical process is still going on. So there's still a dynamic exchange of ions between the solid phase and the aqueous phase. So, and this is why we call this dynamic equilibrium. If we were to measure the solution concentrations of these ions, they would be unchanging. However, the actual process of exchange between solid and liquid would be continuing. And for this reason, you can reach chemical equilibrium, but be far away from isotopic equilibrium for the same reason, because the mineral is still distinct isotopically from the fluid, and it would take a very long time for that process to result in equality of the isotope ratios. But in a general sense, they would have reached actual chemical equilibrium a long time ago. So an equilibrium process or reaction is one which can go forwards and backwards, and we can write generic relations for this. So here we have a generic equation where the reactants A and B, the large A and large B, produce the products C and D. And likewise, C and D can react to produce A and B. The small letters in italics denote what's called the stoichiometric coefficients. And that just means how many parts of each reactant or product are involved in a reaction. Now, for calcium carbonate, which is in equilibrium with carbon dioxide and water, the stoichiometry is 1:1. So 1 part calcium, 1 part carbonate, and so on. And so we can define this thing called an equilibrium constant, K, where the products are over the reactants. And so this hopefully is something that's very familiar to you. The only thing really to note here is that this is a temperature dependent property. And so the value of the equilibrium constant, or to put it another way, the concentrations of the ions in solution versus with a mineral at equilibrium changes as a function of temperature. So it's important to know the temperature of the system in which you're operating. So with an equilibrium constant, what can we do with this? Well, the most useful and most obvious thing to do is to see how close we are with respect to a certain mineral or phase to equilibrium. Okay, so for us, we're pretty much only really thinking most about calcites, perhaps other carbonate phases, but calcite primarily. So the equilibrium constant is already determined. We can look that value up. And so by going into a cave and taking samples of the water and measuring the ions which are present in the water, we can calculate what's known as the reaction quotient, which is essentially the same thing as the equilibrium constant. The reactants and products are the same, and we just simply measure them and populate them into the expression. So that then gives us a means of comparison between a theoretical value of equilibrium and the thing we actually measure in the field. Now, and this is where the saturation index comes from. So the saturation index is merely the ratio of the quotient, the reaction quotient, to the equilibrium constant, and that's to expressed in log 10. So when you get an SI value of 0, that means you're at equilibrium. A more positive value means you're above equilibrium or oversaturated, and a negative value of saturation index means you're undersaturated. And so hopefully that's all intuitive to you, that if you're oversaturated, it's going to cause precipitation of the mineral, most likely. And conversely, if the water is undersaturated, then you're expecting to see some dissolution of the mineral. Okay, and there are other terms which are used interchangeably. One is KSP, you'll often see this, and this is just saying that the equilibrium that we're looking at is related to the solubility of a mineral. So SP means solubility product, but is often just written K, and Q is sometimes referred to as the ion activity product. Okay, so there's both of these terms are quite close and related terms. So, and it's an important foundational principle in aquatic chemistry is this concept of electroneutrality. And it simply states that in an ionic solution, so water containing dissolved ions, which are like miniature charged species, then the sum of the negative charges should equal the sum of the positive charges. And so we can use this as a useful way of firstly addressing how good our analysis is, how good is our chemistry, and then we can use that also to evaluate whether or not the data is suitable for modeling. So because cations should equal anions, then there's this expression here, this thing called the charge balance error, which is it gives you in percent the closeness to electroneutrality that you are. So if you've got a small charge balance error, say less than 10%, for a one-off analysis, that's okay. That's pretty good. If you have a much larger charge balance error, then that's really a clue that you should go back and check your analysis, because often in analytical chemistry, there are some errors or gross errors that can creep in the analysis. If we don't know the composition of the solution we're dealing with, as we never do, we need to have some way of actually evaluating, well, how good is our data or not. So this is a really good, an essential step before you start modeling waters. Also, just to remind you all about units, most of the time when we're getting data, even if we're not doing the analysis ourselves, we send it off to some lab, some commercial lab or something like that. We often get our data back in units of milligrams per litre if we're dealing with waters and fresh waters. And so hopefully you can see on my screen here that the milligrams per litre is sort of on the left-hand column halfway up. And this little slide here was one put together by Ian Fairchild, and it just helps you step through the steps you need to go through to get into the units you want. So if, for instance, you're doing a charge balance calculation, you want to know, does the charge from my cations equal the charge from my anions? Then you need to move across into charge equivalence. And so you would go, say, from milligrams per litre, you would, let's say, divide that value by 1,000, getting you into grams per litre, and then divide again by the formula molecular weights. So that would be, let's say, 40 or so for calcium. So if you had your ppm value of calcium, you divide by 1,000 and then divide by 40, and now you're in moles per litre. Now, to get then into charge equivalent values, it's merely a case of multiplying by the charge on the ion. So for calcium, it would be 2. For sodium, it would be 1, and so on. Okay. So as a workflow to get to the point of doing some PHREEQC modeling, to begin with, you're going to complete your measurements in the lab. So you've already been to the cave, you brought your samples back, you wore your lab gloves, like Sylvia told you, and then you do your analytical chemistry to produce the primary data for modeling. Okay, then quickly check the ion balance, which is, as we've said, this ratio of cations to anions, because yeah, it's a good thing to remember in all modeling. This initialism, GIGO, garbage in is garbage out. So if you're putting crap into the model, don't expect anything amazing to happen at the other end, okay? And then you put it in PHREEQC, hit run, and hopefully learn something useful. So just a quick note on what is actually happening. Like all models, it's only as good as the assumptions that the developers have made, and then the data you're putting in and your understanding of the system and the processes. So it's very possible to do something very unrealistic in a model like PHREEQC. And so I would encourage you, especially if you're starting to do things which are slightly more outside of the range of normal stuff that Speleothem people do, is to go to the textbooks. One good textbook would be this one, which is Geochemistry, Groundwater and Pollution, Appello and Postma. That has a lot of useful information about the geochemical processes that you might want to simulate, but also examples of code, which you can plug straight into PHREEQC. Okay, so PHREEQC is essentially creating a series of functions that describe mole balances for a whole range of different mass balance equations, so equilibria. And the more components you include in a given model, the more complex that series of equations is, and the harder it is to solve. Now, the model has certain ways and means of finding a solution, and sometimes it will exhaust the maximum number of iterations, so how many times it attempts to solve, and then tell you it gives up. And so in those situations, you really need to pay attention to the quality of your data, because if there's something in the data which is a long way from reality and you've just got a gross error, the system will have a very hard time of converging on a solution to the system of equations. But once all those equations are solved, then it calculates saturation indices. And that's basically that's the most basic functionality of PHREEQC. So I'm going to step across into PHREEQC now and my spreadsheet as well. So actually, the first thing I'll do is just bring up the spreadsheet and see if everyone else has the same thing. Okay, so this is the spreadsheet. Hopefully you've all been able to download it. It will sort of open as a Google Docs documents. I would recommend that perhaps you download it and open in Microsoft Excel, because there may be some translational issues there between those two applications. Well, and we just don't really want to do that. So hopefully you've gone through the information that was given to you by the S4 organizers and downloaded PHREEQC. This is the page on USGS where the latest version is hosted. And you hopefully downloaded this GUI version, phreeqci. So the first exercise is this one, example one. And we'll see how we go for time. It may well be that we only manage to do this, which would be fine. And if we've got time, then we can look at the second example there. So the spreadsheet here shows a series of drip water measurements done on Waipu in a cave, as well as the carbon dioxide, atmospheric carbon dioxide concentration for the months that where the samples come from. And you'll see that we've got temperature, pH, etc. across here. And you may also notice, for those of you who have sharp eyes, that there's a column here, S with a bracket 6 there. So that is PHREEQC notation. So in PHREEQC, it recognizes sulfate by the element at sulfur, and the number is the oxidation state of sulfate. So there's a few things in the code which are kind of like nerdy stuff that you might not know. So that's fine. But that's why it's there in that form. And you'll see that I have added comments throughout the spreadsheet, so you can hopefully make sense of this, perhaps in your own time. So I'm gonna stop sharing the spreadsheet. I will be using the data in it. And so hopefully you can all follow me. I'm just gonna go into PHREEQC now. Okay, so hopefully you see PHREEQC. Seb, can you see that? Not in... Maybe, yeah, that's awesome. Good. All right, so this is the sort of landing page for PHREEQCi Interactive. When the organizers asked me to give a workshop on this, I did have a little panic because I haven't used this version of PHREEQC, but I thought, well, you know, maybe it's a chance for me to learn something new. I'm getting a bit set in my ways, but you know, old dogs, new tricks and all that. So PHREEQCi is essentially just a GUI which sits on top of PHREEQC. So the code itself isn't any different. It's all there in the background. What the interactive version does is it actually makes it a lot easier and a lot quicker to get started, which is you know, not a bad thing. The main reason I think it's good is that it will prevent you from making errors in syntax, which is the particular language the code is written in, or the particular language the code is expecting you to write. So if you don't know that, then you will continuously get tripped up by syntax errors. So this is actually a really handy thing. So to begin with, let's start by defining a solution. So in its most basic form, PHREEQC is essentially simulating reactions that you could think of as happening in a beaker, or here in a little volumetric flask. And you'll see on the first screen that comes up is that it's asking for the general solution conditions that are present. So I'm going to take my data from Waipuna, and the first row of that data, which is 18th of October 2016. And so the cave temperature, I'm just going to start entering values, 4.4. pH was about 8.3, which sounds about right. And then there's a few other things in here that would pay us to look at. Water mass, 1 kilo per liter, which is the density of fresh water. Saline water, ocean water, has a slightly higher density, and so this is where this is pertinent. And indeed, I can think of examples of caves which are truly karstic caves, but are in the coastal zone, where waters can be rather saline, actually. So this is something that, as an assumption, value of 1 is probably right 99% of the time, but there will be exceptions. PE is an important one. So the PE is the, like pH, it scales in the same way. This is the negative log to the base 10 of the electron activity of the water. And this is something which is not really, hasn't really been touched on in Speleothem science to this point. There's a rather coarse assumption made pretty much by everybody, either knowingly assuming it or unknowingly assuming it, that the water is oxidizing. Okay, so because caves are in the vadose zone and the cave environment itself has lots of oxygen in the air, you could make the assumption initially that the water is indeed in the same condition, but no one has ever looked, I don't think, as far as I know. So it could well be that drip waters can be rather reducing. And that's a term that means that the electron activity is higher than what you would expect for water in contact with oxygen in the atmosphere. And certainly, as you go beneath the Earth's surface, there is a tendency or a trend towards more reducing conditions. And I've certainly seen evidence in Speleothem's for redox chemistry taking place. So I would say, in addition to what Sylvia said about nanoparticles and nanoscience being at the research frontier in many disciplines, I would agree with that. And I would also say that, but in Speleothem science, there is actually a large number of quite well-established areas of science which are yet to really be looked into. And one of those you could broadly classify as biogeochemistry. And within biogeochemistry, you have a lot of processes which operate on trace elements and on other elements, right? So there's a lot of processes and science to be unpacked just looking at the pretty basic redox processes. So I'll stop there on redox. I might have time to come back to it. Okay, so let's keep going. So that's the general inputs. Now individual element input. So this is just a point and click exercise. So the first thing to do, as I mentioned, is to get the units right. We are using ppm values or milligrams per liter values. Okay. Milligrams per liter in fresh water is the same thing as ppm. Okay. And looking at my spreadsheet, we have the sodium, potassium, calcium. So I'm just going to populate this in that order to make life easier. Sodium, potassium, calcium. This list that I'm clicking on is just alphabetized, so it doesn't work in the way that my brain works, but that's fine. Magnesium is over here. Chloride. And alkalinity. So it is in the database as alkalinity, so you can just click that. S6 is sulfate. And I'm pretty sure in here it just says sulfate. There you go, that's sulfate. Put that in there. And I'm going to ignore the carbon dioxide for now. Okay, so let's leave it like that and just hit OK. And so what it's done is it's just populated into the scripting window all of those components which we just clicked on, and it's written it in the right format. Okay, so you're probably wondering, why didn't you type in the values? Well, I'm just going to type them into the scripting window because I think that's slightly more convenient here. But you can also use this solution window here to do the same thing. So over on the left, there's a navigation pane, and you'll see solution 1 is sitting there. So if I click on that and hit edit, then all of that information I just played around with is still there. So I could write into this concentration column here all the values, but I also know that if I type in here, it's basically the same thing. So, okay, so sodium will be 5.2, potassium 0.2. And alkalinity is 155. Sulfates 3.1. So that should be enough information for PHREEQC to be able to start doing some calculations. I'm just going to save that. Generally speaking, PHREEQC doesn't like it if the script isn't saved before you try and run it. This is me for force of habit. So now we should be able to run it, and you'll see that this in blue over on this menu is run. So I'm just going to have a go and see what happens. So it's already completed the first calculation. All right. So I'll close that. Now, if you look across to the left-hand side of the screen, in addition to the input file, which is still there, and the database file, there are now additional tabs, one of which is output. Okay, so this is where PHREEQC dumps all of its calculations. All right, there are ways and means of selectively outputting things, and it's called selected output. I probably won't have time to talk about that today, but to begin with, if you can just familiarize yourselves with this output page, and there's actually a lot of useful information in here. So that's the initial input data, and then scrolling down, it's identifying the composition of the solution and calculating it out in molar values. So we gave it ppm values, but it's calculated it into moles. And this is one of the things that doing geochemical modeling is quite handy for, is it saves you from doing conversions, it saves you from making mistakes in these conversions. So it's quite handy in that respect. So these are our mole balance expressions getting set up here. And then there's the general description of the solution here, pH 8.3, PE of 4. PE is this electron activity term, and it's saying, I'm assuming that the solution is fairly oxidizing. Okay, so present in an atmosphere with oxygen, okay, which is a fair assumption probably. Then it goes on and calculates a whole bunch of other properties. An essential one to look at here is electrical balance and the percentage error. And you see here that it's telling us that it's slightly out of balance. So as a percentage, my analytical chemistry is not bad, could be better. So -6%. And so that tells us that it's out of balance, and indeed there are more anions than cations present. And that's not correct. In the real world, there's actually equal amounts. Okay, so that's something that's to bear in mind. And then it starts to do these speciation calculations, so-called. We have the elements in series, starting with water and then carbon. Okay, and so in this solution, it's saying, well, I'm assuming there's only carbonate species present. You've told me there's alkalinity. Alkalinity, for those of you who don't know the term, is the same thing as dissolved inorganic carbon. That may be a term that you're more familiar with. And so you can see the various species of the carbonate system here under C4, right? So C4 is the oxidation state for the DIC, and then it's listing all the different species. The most in the order of abundance. So the most abundant species here would be bicarbonate, and that shouldn't be surprising to those of you who know about the pH dependence of dissolved inorganic carbon, that at around pH 7 or 8, bicarbonate should be the most abundant species of carbonate. Okay, so each element is listed in turn. These values are molar values, and in addition to the molar values, which is the first column here, there are other measures which you will find increasingly less useful. The second one to the right of molar is activity, and this is a very closely related term. And what effectively activity is saying is, what is the concentration of the ion in question, which is available or active and able to be involved in reactions? Okay, it's a very important concept that just because something is in solution and you can measure it doesn't mean that it's going to react necessarily. It actually could already be busy, you know, it's having a conversation with some other thing and isn't available to get into the reaction that you're thinking of. So the calculations done by PHREEQC uses activities. And so there you have it. You have all of these different species that could be present. So there's magnesium 2+, but then there's also magnesium carbonate and so on. And then at the very bottom here, we have the saturation indices. And this is where things get more useful and interesting for us. We see here that in addition to a whole bunch of mineral phases that PHREEQC has identified could potentially be in equilibrium with the solution, is calcite. Now, here's a note on the pitfalls, potentially, of taking these numbers and interpreting them as if they were just the gospel, you know, that this is how it is. This is just a simulation, okay? The calcite one is probably quite close to the real world, and others possibly a long way away from it, because and interestingly for Sylvia, perhaps, there's a couple of saturation indices here, dolomite disordered, dolomite ordered, and they have different values, right? And they're both, it's saying that both of them are undersaturated, the negative saturation index, but the ordered one has a lower value, sorry, a more positive value, which means that it's closer to equilibrium or might precipitate. But that's misleading. The thing is that whether or not something is likely to form and the degree to which it's saturated or undersaturated also has to do with its energy of that phase. And if it's more ordered, more crystalline, it has a lower energy, then then PHREEQC will calculate that it's more likely to form, for instance. But actually, the process by which you get there could take a very long time or might not happen at all. The calcite in this context is more well behaved because it precipitates rather quickly, and it can precipitate under inorganic conditions. You don't have to have other types of things in the water to induce precipitation. Okay, so we can kind of take these calcite saturation indices at face value. All right, so that's the speciation, and that's what the output looks like. So if we go back to the input now, we can see that firstly the water was slightly, or my analysis of the water was slightly wrong, that there was more charge from anions than cations. Now, this is the sort of thing that, this is where knowing something about geochemistry is helpful, because it sort of stops you from doing something erroneous. As a rule of thumb, when you have a system of water which is not charge balanced, and you're dealing with the carbonate system, then it's okay to play around with sodium and chloride. The reason being is that their contribution to the crystallization process is very sort of peripheral, not really involved, and they're really just you know, kind of they're there, but they're not really they're not involved in any processes that we really care about. So we can adjust these values to get the water to electroneutrality. And I know that it's slightly too many negative ions. So what I'm going to try and do here is type in charge for the chloride rather than the concentration. I'll see if it likes that or not. Yep, contains input errors. Didn't like that. There you go. So what I'm going to do is I'm going to give it some amount of chloride. The original spreadsheet value was 12.4. Another thing that gives us some confidence that we're not doing something totally crazy here is that in general, the solution, the drip water has quite consistent chloride concentrations of around sort of 10 to 20 parts per million. So not big numbers and fairly consistent. So what I'm going to do is tell phreeqc, well, you've got 5 ppm of chloride, and I'm going to ask it to calculate the charge balance. So sorry, to adjust the charge balance for chloride. Now, being as this is a PHREEQC workshop, let's actually do this using the PHREEQC interface. So I'm going to go here, edit, and over here, charge balance. Notice here there's a little drop-down menu. This gives you the ability to balance the charge of your system with any of these components. And I'm going to choose chloride. Okay. And now you'll notice that it's made a couple of minor adjustments and that charge has appeared next to the chloride value. Before, what I did was I thought, oh, well, I'll just tell it to adjust the charge with chloride, and I gave it no chloride to work with, and it threw out an error. And that's because I wasn't doing it, you know, I didn't put the syntax in properly. I didn't give it what it was expecting. The GUI hopefully didn't make the same mistake. So let's try. Yep, that was fine. So the GUI has proved its worth, and we can see now what was the original calcite value, saturation index. Well, I think it was pretty much the same value, which means that the minor adjustment we've made, because the system is now is electrically neutral, it's balanced, it didn't make a big difference to the chemistry. But it's important that we're dealing with electrically neutral compositions when we do our modeling, particularly when we step away from speciation modeling in PHREEQC and start to do more sophisticated things, because the code is looking for and demands that the system is balanced. Okay. Right, so that's the first one. So all we've done is we've told PHREEQC there's some water. We've given it some boundary conditions, told it what's in the water, and that's it, right? Now, we know that in a cave system, actually, there's more to it than that, that there is a gas phase at least present, the cave air. So let's try and make this slightly more realistic by incorporating a gas phase into this calculation. So if we go back to our Explorer, solution 1, and edit it, we can then step through, oh, sorry, no, my bad, sorry. Rather than going here, go back to the scripting window, and this is where I just need to play around a little bit to get it right. Okay, so you'll see that these icons are populated again. They were grayed, and now they're populated. So I need that to be able to use the interface, and I'm just going to hover over them and see what the different ones do. So you can see that there's lots of different sorts of chemical reactions that you can simulate, okay, including the incorporation of a gas phase. Just going to check what I did before. Yep. Okay, so I'm going to hit the gas bottle. All right. And over on in this menu, you can see that there's a bunch of different gases that are present in the default database of PHREEQC. Now, the databases aren't something I've discussed at this point, but just to know that what PHREEQC is doing is it's using a reference database for all of the thermodynamic constants that are used in the modeling. We just give it data on what's in the water or what's in the air, but it uses a whole bunch of other data and other constants for these equilibrium calculations, and they exist in the database. There's a bunch of different databases. The default one is just called PHREEQC. The other databases have all sorts of other components in them, which may be of more or less relevance to you. So we're sticking with the default database for now. And in here, we're just going to select carbon dioxide, okay, and going to put in its partial pressure in atmospheres, okay. So the first thing to do is go back to our spreadsheet and just check what the carbon dioxide pressure was at that time. It's 443 parts per million, okay. Which should be a PCO2 value of, basically it's 10 to the minus 4. So that's the equivalent in ppm in atmospheres. So that's 443 parts per million in atmospheres. Okay. So I'm just going to hit OK, and that's popped up there in the scripting window. And I'm just going to organize this the way that I would normally do it. I like to have my solution at the front before I tell PHREEQC there's a gas present. I'm also going to put in a little bit of pseudo code here just so that we know what we're dealing with, because it's so easy to get lost. Okay, so this is Vaipuna 11 from the 18th of October 2016. All right, let's see if this runs now. All right, so skipping to the output, everything should be as before. The percent error is still 0, and the components are as they were, and the calcite value, the saturation index, is still 0.57. Okay, right. So what that means is that the default value that PHREEQC is using for gas pressure is pretty close to what we just told it is present. Okay, certainly for when it comes to the carbonate system, it's not our adjusted value that we've just put in, doesn't really make much difference. Okay, so now we know that the solution is oversaturated. It's got a saturation index of 0.57. And we've got the gas phase now represented with carbon dioxide present. And now what we want to do is use these this information to then work out how much calcite might be deposited onto the speleothem. Okay. So what we're going to do is go back here to the GUI. I'm just going to see if I can't. Yep, that's all come up now. And I'm going to hover over these icons until I see the one that I want. Use. So that little arrow there with the sort of curved arrow is use. So I'm going to click on that. Okay. And I want to use the solution. Okay, number 1. That's what I want to use. Okay, so enter that. Again, it's popped up at the top. I'll just pop it down at the bottom. Okay. And then we're going to introduce what's called an equilibrium phase. Okay, equilibrium phases. And that's the helpfully identified forwards and backwards equilibrium arrow there. Hopefully you can see that. I'm going to click on that. And now there's a whole smorgasbord of phases for you to choose from. I'm going to be very, very boring. And I'm going to put calcite in there, if I can find calcite. You're probably all yelling at me, it's over there. There it is. Okay. All right, so hit OK. Put use solution 1 there, and calcite and now just at the end of the script here, I'm just going to tell it to stop. I'm going to give it an end. That full stop there is end. Okay. So just stepping through what the script now says. It says I've got some water. It's 12 degrees roughly. These are the conditions. This is what's in it. There's a gas phase present, the CO2 at 443 parts per million. Please use solution 1 and equilibrate it with calcite. Okay, so we're telling it that there's calcite potentially present. Okay, so just to break down what this says here, it says calcite. Okay, then the next number is the saturation index that we would like the water to find. So we basically we're telling PHREEQC, find the solution composition that gives us a saturation index of 0 or at equilibrium. Okay, we already know that the water is 0.57 saturation index, so it should precipitate calcite. But just in case, there's 10 moles of calcite around. So that's what that 10 is there. So if the water was undersaturated, then it would dissolve some of those 10 moles into the water. Okay, so it's basically there is a contingency, but we know the water is already oversaturated. All right. So I'm going to save that again and run it. All right. And we can step through what the code has done. So same as before, read in the solution and calculated the saturation index. Now it's doing what's called a batch reaction calculation using solution 1. It's saying, okay, what's present? We've got a phase assemblage. Okay, so it's only one phase because we're keeping it simple, but you can see that actually you can start to incorporate multiple minerals, multiple phases, multiple gases. Things can get very complicated very quickly. So it's all possible, but it's best to start simple and build and such things. So we've got calcite, got the solution, and then it calculates the solution composition for a calcite saturation index of 0. Okay. So by looking at the value of calcium in the initial composition, it's going to make a note. And comparing that to the calcium after equilibrium is reached 1.075. So we can see that certainly there's an amount, and this is molar, so it's initially hard to maybe intuit what this means, but there's certainly less calcium in the water now than there was at the beginning, right? So what I'll do is I'm just going to stop sharing PHREEQC for a second, unless maybe I can share multiple screens. Is that possible? No. Actually, let's not go there. I'm enough of a technophobe as it is. Let's just go for go into the spreadsheet. Here we go. All right. So hopefully you can see the spreadsheet. So I've put in here. Put your output data here, right? So for initially, we got the saturation index value of 0.57. And then I've got calcium initial, calcium final, right? So we can put our values in here. So that was So I should probably put another column in here to convert this. I'll just convert this into ppm units quickly. So it's lost 3 ppm, sorry, 3 milligrams per liter of calcium out of the water, right? And sort of then we sort of look at what was the initial calcium. Well, it's 46 ppm, so it's lost something slightly, something slightly less than 10% of the calcium, right? Which seems like a reasonable thing. Obviously, this is assuming that the water's had time to sit around and reach equilibrium. But in a Speleothem context, for a stalagmite, the water's only on the top of the stalagmite for a certain amount of time. And so it may well be that not all of that calcium was indeed lost in the real system, but it gives us an idea. And so what I'd like you to do, and probably this isn't the forum to do it, but you can have a play, and then you can email me your results and see if you got the same results I did. Maybe you should do that if you've got nothing better to do with your lives. So there's in the spreadsheet, you can see there's a whole load of rows here, and through this data series, the CO2 concentrations varying quite a bit from sort of basically atmospheric background values through to sort of close to 1,000 parts per million. And the question is really that I would pose to you, if you would like to have a look, is to see, is there a particular seasonality to the deposition of calcite in Waipuna Cave? And if that's the case, then perhaps the Speleothems have a certain bias towards a particular season. Now, as we go through in the spreadsheet, you'll see that then it starts to get patchy. So the data series here was okay, and then I started to miss some analyses for various reasons. And so we don't have values of alkalinity for the last 4 measurements. We don't have values of sulfate for the last several. So you might think, oh, well, let's just throw this out. We can't use these data. But actually, it's probably quite reasonable to still use these numbers because if these red values here, these represent the median of the prior data. And sulfate, for instance, is really quite stable, all right? As is chloride, really quite stable. So you can go through a process where you actually can start to converge on the correct value of alkalinity, because the other two are quite well constrained. They don't change very much over time. So, and a way to go about doing that would be to initially just evaluate how far away from equilibrium each of these samples is, putting in some default values for chloride, sulfate, and the alkalinity. The deviation from electrical neutrality would then tell you how many ions you need to add. And you can see that really the chloride and sulfate aren't changing very much. And so that deviation is probably reflecting the alkalinity, so the dissolved inorganic carbon. And that is a strategy that's used by a lot of people in Speleothem science, who either, for one reason or another, can't do all of the different ion analyses that are in a system, right? So often it's quite straightforward to do cations. You can take an aliquot of water, drip water, and send it for ICP-MS analysis, and you'll get the cations. The anions are harder to do, perhaps, and so sometimes you might not be able to do the alkalinity because that requires a reasonably large volume, and it's a titration process. So what you can do in those situations is measure the other anions, chloride, sulfate, etc., nitrate, and then infer the concentration of alkalinity that's present. All right, and that's a strategy that is employed a lot, but and it's because of reasonable expectations, right? That the host rock is limestone, that the water therefore is going to be mainly have calcium and dissolved inorganic carbon in it. So those are things that you can still do even with incomplete data. All right. So let me see, how are we doing for time, guys? Do we, are you happy for me to carry on, Seb? Yeah, just keep on going. All right, sweet. So let me bring it back to, you should all still see my spreadsheet, hopefully. Right, so example 2 is mixing corrosion. I thought that might be something that would be worthwhile looking at. Mixing corrosion is a process which is quite intriguing. This is hopefully you can see this this photograph here. This is a picture of a cave entrance in Fiordland in the south of New Zealand, and there's a series of caves here on this mountain which are mostly dissolving. So the speleothems in them are probably not active for the majority of instances. There are some places where there's still active deposition, but also there's extensive corrosion of the cave systems here. And that's surprising given the conditions that are present. There's abundant vegetation, certainly lots of dissolved organic, carbon dioxide. So why are the cave formations dissolving? And my suspicion is it's got something to do with this process called mixing corrosion, which you may or may not have heard of. So in principle, what you have is 2 solutions, both of which are have dissolved inorganic carbon in them and are at or above equilibrium with respect to calcite. But when you mix them, you end up with an undersaturated solution. So that's something which is a strange concept to me, like you can start with 2 solutions which are distinct but in equilibrium with calcite, mix them together and get something that's not in equilibrium with calcite. While it's not intuitive, it's true. So what we're going to do is have a crack at doing that. So I'm going to stop sharing this spreadsheet, and I'll step across to PHREEQC. But this is the page of the spreadsheet which I'm working with. Okay. So. Okay. So I'm going to go back to the input and let's start a new experiment. So I might just delete that last one. If you're worried about losing this code, don't be. The code is pretty much there in the spreadsheet already. I included example codes for these 2 exercises in there, so don't fret. All right. So firstly, we have to define a solution. That's where it always starts, right? So let's start with this, and I'm going to leave the temperature at the default of 25 degrees Celsius. pH 7.1. And PE of 4. Yeah. Okay. Now in the inputs here, I'm going to actually leave it as the default units of millimolar. Okay. Because that's what I've got in my example. And we're going to incorporate carbon. And this is going to be basically, this is carbonate. You get the same thing if I did alkalinity. So it doesn't actually make any difference to PHREEQC. And calcium. Right. And the carbon dioxide, that is going to be, we're going to put in here the saturation index for calcium, for carbon dioxide. So I'll explain what that is in a second. So the saturation index for a gas is the same in the same way that saturation index of a mineral is the log 10 value of the ratio of the quotient to equilibrium constant, if you remember that. Well, saturation index of gas is just the base 10 logarithm of the gas pressure. So basically, it's just it's like the ppm value CO2 to the log 10. Okay, and in here in phase for calcium, I'm going to write calcite. If it actually likes that. Yeah. Okay. If I hadn't typed that in, let's see what this drop-down menu gives us. Oh yeah. A whole bunch of different things in here. So a whole bunch of different minerals and things that you can ask it to get calcium from. I'm saying let's get calcium from calcite. Okay. So let's just enter that. Oh, expected saturation index. Got it. Right. We want it to be at equilibrium, right? So we want a saturation index of 0. All right, so let's see what have we got here. So the carbon is currently 0, and that's not quite right. So I made a bit of a boo-boo there. I need to edit my my solution again. So I've told it the concentration is 0. For calcium, it's fine. It's going to get calcium from the bedrock, but it needs some carbon in here. So the phase, we're going to tell it a phase is CO2. I'm just going to see if it comes up. Yeah, CO2 gas. So that's quite helpful. As you type into this cell in the drop-down menu, it starts to eliminate possibilities. So if I typed in, I don't know, if I just typed a C, it's going to give me everything that has C in it, right? But if I go CO, then it's eliminated a whole bunch of options, CO2 gas, right? And then in here, I'm going to go minus 1.5, which is a sort of a higher, it's a relatively high value, sort of percent level CO2, okay? And let's so let's see if that, firstly, if it runs. Just save it quickly. Okay. Yeah, so it ran. So this is this is a lot smoother than normally when I'm doing PHREEQC modeling. I'm typing things in and getting it wrong. So the GUI actually is really helpful to avoid those pitfalls. Okay. All right, I'm going to start putting in a little bit of other text just to give us some reference if we look at this in the future. Some corrosion. Okay. Solution 1. Now that the code is, or the GUI has generated the code in the correct way, I'm just going to copy that and I'm just going to modify it now. So this is going to be solution 2. And what else do we want to do? Oh yeah, so we're just really going to leave it the same. We're just going to give it a different gas pressure. Okay, so different gas pressure for the carbon dioxide. All right, and I'm going to type N here just to make it easy and quick, and I'm going to run it. Okay, so first off, let's have a little look-see. All right. So because we've given PHREEQC a limited amount of information. It's set, we've told it like, all right, you've got water, it's 25 degrees C, and you're going to get some you've got carbon dioxide and you've got calcite, right? Well, it's produced, so the initial assemblage for this water is actually out of balance. It's not electrically balanced. It's quite strongly out of balance. So minus 22%. So not great, okay? And so we can tell it to get into equilibrium or become electrically balanced so that the calculations are done properly, right? So what I'm going to do is after this pH 7.1 here, I'm going to tell it charge, and the same after the other one. Okay. And hopefully it doesn't disagree with me that that's the way to do it. Yeah. Okay. So now it's brought it into charge balance by adjusting the pH. So you can see that in here you could use a number of different components in the water to drive it towards equilibrium or away from equilibrium, to be charged or uncharged, etc. So it's a very flexible code with a knowledge of what what the reasonable constraints are on it. So okay, so that's good. It was balanced. All right. And let's just check here. Okay, so it's not dissolved any calcite here. And I'm just wondering, oh yes. Okay, I'm just looking at my notes and then remembering. Okay, so we're going to introduce an equilibrium phase. Okay, so it can do the calculations. Okay. Right. So evidently, I can see now the problem. Okay. So this is the trouble when you're doing things on the fly. There you go. All right. Just looking at my code here, I've told it, hey, get calcium from calcite, but I've not given it any actual calcite. It's a 0 after that. So I'm going to give it some actual calcite. So that number that falls after the calcite there is the amount of moles of calcite that's present that the water can interact with. So if with a 0 in place, then, well, it's not surprising there's no calcium in the water. Which if we skip to the output, I haven't run the script again yet. So you can see that in the water, all that's present is water and undissolved oxygen, that's all. All right, so let's try that again, run it. Okay, right then. So we are again balanced with, and it's used pH to do this. Okay. Okay, and here's our phases. Okay, and now it's doing a reaction. Yeah, so initially it was just read in the script. It said, okay, I've got pure water, and then it starts the reactions. Okay, so now it's saying, okay, I'm reacting it with calcite, and I've got carbon as well. So there's the carbon. It's still finding electrical neutrality, so that's good. So it's adjusting the charge balance, and interestingly, the PE is driving negative. And the pH that's achieved in balancing this system whilst maintaining equilibrium with calcite is a pH of 9.9. Okay, so basically what I've done to excuse my coarse language is I've put in a shitload of carbon dioxide and dissolved a lot of calcite in the process, and that's caused it to get very, very alkaline. Okay, that's that solution. Okay, so it looks to me like it's just done the solution 1 reaction, and that's because I just had equilibrium phases 1 here. If I do the same thing for the solution 2, so now it's equilibrium phases 2, all right? So you see you have to have the same numbering for between solutions and phases. Okay, let's run that. Okay, so skip down. Oh, what's happening there? Okay, so I'm not entirely sure why it hasn't run the equilibrium phases command for solution 2. And this is why I started with the caveat, I don't necessarily think I'm an expert in PHREEQC. The coding for these things can take a while to sort through. So what I'm going to do actually is I'm just going to take the script which I prepared earlier and try running that, because these little errors can creep in and it can take a rather long time to work through them all. So let's try running that. Excellent, good. Right, so let's have a little look at that output. So this is the script. I just ran the script which is in the spreadsheet as the example script, which I put together without having performance pressure. There we go. All right, so that's fine. Both initial solutions have calcium in them and are in equilibrium with calcite, which is as it should be. Okay, right. Now it's doing this mixing step. So I'm going to go back to the input and show you how this gets entered. All right, so I'll just, this hash just means ignore this line when it's running through the script. Okay. So to mix two solutions together, all right, I'm going to go back to here. All right, and mixing, let's find mixing. There we go. So that little flask with a plus is mix, okay? And so it can tell that we've already defined two solutions, all right? So I'm going to select both of them. And then it's a matter of just telling it what fraction of which solution you want to include, right? So in the example I've got here, I'm using 0.4 and 0.6, right? Okay, so you can see that the GUI is basically dropped into the script the same code as I had before, all right? But that's the function in the GUI that gives you that code, all right? So if I run this, hopefully it all goes smoothly. All right. So as I said before, the code creates two solutions. Solution 1 and 2, both are in equilibrium with calcite, which you can hopefully see from these zeros in saturation indexes. And then it mixes them together and then recalculates the new solution composition, right? So the initial solutions, pH 7.6, pH 6.9, the final solution 7.1. It is balanced, it's still electrically balanced, which is as you would expect. And the resulting mixture has a negative saturation index. So this really sort of exemplifies what can happen, is that you can have two waters or two flow paths which have distinct carbon dioxide inputs. They both evolve to equilibrium, but upon mixing of those two saturated solutions, you end up with an undersaturated solution entering the cave. And the end result would then be that you would be seeing dissolution of the formations as opposed to precipitation of the formations. And certainly this is something which we do see evidence for quite broadly. And indeed, even within one chamber of a cave, you could have as an area where there's active dissolution, and another part of the same chamber, we have active precipitation. So this is really just to illustrate the principle of entering the code, and that the code can simulate it with a knowledge of n-member compositions, okay? So here we're just making up numbers, but equally you may be able to sample waters which allow you to find some n-members and then start to play around with mixing them together. I'm just going to quickly stop sharing and go back to the spreadsheets. It's that one. So hopefully you can see on the screen there, I've got a graph. Don't know if that's come up. Let me see, it should be. And so I've just calculated the saturation index in PHREEQC with different mixing proportions. So as a percent, on the x-axis, this would be the percentage of solution 1 in the mixture. And really, there's no mixture that gives you a saturated solution. Actually, all mixtures produce undersaturated solutions, which is quite surprising, not necessarily intuitive, but there you are. So I think what I might do is just finish with some concluding comments about PHREEQC, and then put it to the floor, hit me with questions, and we'll see what you have to say. So I've included in the spreadsheet a tab that says README, and that gives you a pointer to the textbook or the PHREEQC user guide, and some other notes on the functionality that's in the code that you can access. So I should maybe talk a little bit about, or to orient you a little bit on the screen, on the PHREEQC screen again, so that you can go looking after this workshop's done. You can look for yourselves and start to become familiar with it. There we go. Okay, so you have the GUI, which gives you the ability to, create new solutions, and add in different commands to do different sorts of reactions, right? The code has the ability to do a whole suite of different sorts of reactions, including chemical kinetics here. So you include rate expressions. It is possible to do inverse modeling. So you say, okay, well, I'm starting from this. I have this solution that I've measured. And I suspect that it's the result of mixing. So you can then infer or do inverse modeling to try and simulate the composition of the original solutions that mixed together. So it would be the inverse of what we were just doing. There are reactions where you can add, do batch reactions. What have we got here? Yeah, so if I click on reaction, it gives me the ability to add in a component and say how much of that to add, and then in what, how many steps and so on. So you can actually tell it to add a reactant of interest, let's say carbon dioxide, at a prescribed series of steps with a prescribed concentration. Yeah, and so there are many other options, including transport. So here at the end of these little icons, there's advection and transport. So the code can actually start to sort of evolve a solution with respect to the composition of a solid phase or the matrix, and move that through that matrix as a function of time. So the code uses time to determine how fast these steps occur. And that is where you, as the sort of expert with the knowledge, say, okay, well, this is what the flow rate of the water is, or what we think it is. So there's a lot to it. It's a very mature code. You can do a lot with it, with a good understanding of the fundamentals. Now, so we've looked at input and output. I'm just going to quickly touch on database. So here is showing the Mix4 database. And that includes a whole variety of other ions and components which we've not touched on today, but which PHREEQC can handle. So including iron, manganese, mercury, all sorts of stuff, all sorts of organic compounds, which, just harking back to what Sylvia was saying about organic matter and its relevance, certainly is. And you can start to incorporate known, well-defined organic compounds here. So for instance, let me see, citrate, which is a simple carboxylic organic acid. There's also expressions for different dissolved organic matter components and so on. So so this is just the database that PHREEQC is drawing from. And within this, there are the components, the different phases, etc., are all defined here. So if you can do Control F and just do a search, and you'll see, okay, well, under phases, I've got all of these possible phases the water could be equilibrated with. You know, if you're not sure if the mineral you're interested in is in the database, just do a find, you know, and look it up. So I don't know, aragonite. There it is. Okay. While it's identical in terms of its chemical formula to calcite, its thermodynamic constants differ. Okay, so this is why PHREEQC would give you different results for aragonite versus calcite, and so on. So the other great thing about PHREEQC is actually that if it doesn't exist in the database, you can just create the database entry in the input file. You can just add it in there. So that's actually something that's doable as well. So you're not limited by things not being in the database. So because the database that we're using here is this mix 4 one, and I'm a long way from the top. So mix 4 up here. That means that there's all of these components are accessible via the GUI to add into the solution, right? So, oops. So let's say I want to create another solution. I'm just waiting for it to decide to play along. Oh, it's because I'm in the database. So this is where me being a non-GUI user, I fall over. Okay, I need to go to input. There we go. Okay, so in here, if I click on the solution, you can see that in here there are a bunch of options, and including organic components. So you could say, actually, I think that I would like to know what will happen to this trace element and how it behaves if I include, say, citrates, right? So we can add citrate directly from here, right, and put in the concentration. And then PHREEQC will then actually simulate what will happen between the trace element of interest and the citrate molecules. And so obviously in a real cave system, you can't expect that citrate is present, but dissolved organic matter is present, and dissolved organic matter with properties which are not too dissimilar to citrate, right? Equally, you can use it in designing experiments, lab experiments, where you're controlling the components that are within the mixture. So there's a lot of additional functionality that's present. Now, that's coming up because I've told PHREEQC that we're using the MinTech database. So here it says set default database, and I have already sort of told it what to use. But if you hit on that little icon, so I'll just go back, this 3-dot little thing here, you can see all of the databases which are present in PHREEQC that are available. So it's a matter of just going in here and selecting one. And popular ones are PHREEQC, Vortec 4F, and the MinTech one. However, as you see, there are other options. Tipping and Hurley refers to a database which is designed to look at cation binding by organic matter. So, you know, that would be for a particular niche application. Most of the time for what you'll want to do. So if you want to use PHREEQC just to calculate saturation indices and to work out, is my drip water saturated or not, then the PHREEQC default database is fine. Okay. if you run into trouble and you're entering things incorrectly, have a look at the errors tab. It should give you some insights into what's happening. And otherwise, I would point you at the help tab here. So you'll notice that under help, there's several different things you can look at, but user guide for PHREEQC is actually, there's an electronic version of the user guide here for you to explore. And you can see that there's a bunch of introductory and then more detailed information about the code, and then more information about the different commands that you can draw on and example code of how to implement them. So a good example here is equilibrium phases. So it will give you an example of a script that you could enter, right? And then breaks it down and what each part of the script is actually doing. Okay, so really this is a very helpful guide to getting started with PHREEQC modeling. So with that, I guess I'll stop sharing and I'll pass it across to Seb or Elizabeth to take over.
Yeah, thanks, Adam. That was super helpful. It's intimidating at first, but it's really helpful to see someone like run through it. Definitely pulls down that barrier a little bit. All right, so are there any questions for Adam?
Stunned into silence.
Well, you've provided so much information that I think it'll be a useful sort of starting point for anyone who wants to dive into it.
Yeah, absolutely.
Okay, there is one question in the chat that is, what about the use of isotopes?
I was afraid someone was going to say that. I don't actually really know. I've never tried. It is in there. It's clearly in there. So I'll go back to sharing mode, and I'll share with you what I do know, which is embarrassingly little. So in the input, there is the potential here to incorporate isotopes. So under solutions, you'll see that there's a tab here, isotopes advanced. And actually, in principle, we could start to incorporate carbon, the different isotope systems that are most certainly common isotope systems. So carbon isotopes, carbon-13, delta-13C, oxygen isotopes. The code is going to, I'll just dump this in here somewhere. Yeah. So I've just dumped this into the script. It says solution 3 here, and then there's a dash isotope 13C, and then a value after it. So to be honest, I'm as new to that as everyone else. I'm sorry, I'm not an expert in this, but what I would assume is the model would calculate the isotope ratio. Let's say if you're precipitating, then it will calculate the isotope ratio of the residual carbon in the solution based on the equilibrium fractionation factor, right? So therefore, you need to know, need to look into the database and see what fractionation factors involved in there. And then also recognize that this is an assumption of equilibrium. If you want to incorporate kinetic fractionation, which actually would be more useful probably for carbon, then you would need to incorporate a rate expression which allows for the kinetics of that reaction. So it's in here, but I actually I'm embarrassingly uncertain about that. So I'll just have a look and see. Isotope. So this is the isotope expression. Isotope ratios. Here we go. Okay. Yeah. I'm not going to read this in front of you, but there's a lot of information in there in the help. if you would like to try and incorporate isotopes. I know that Appello and Posma in their book, there's several examples incorporating isotope ratios too. So all I can really do is commend you to look at that literature and also look in the help